Okay. Can you see my screen?
Not yet. Yeah. 1 second. Yeah,
how
you
about,
should begin now. Go for it.
okay. Okay. Okay, thank you for your introduction. Hello, everyone. I would like to present our paper with the title, A Second-Order Programming Approach for Simulating Biphasic Materials. I'm Pengbin from University of Montreal. Natural material and human-made materials exhibits complex stress-strain responses characterized by strong nonlinearities and direction-dependent behavior. For example, due to the Young-level structure, many textiles initially exhibit only weak resistance to deformation, but stiffen rapidly beyond the direction-dependent threshold. Another extreme example is given by this chairmail. One way of modeling this biphasic behavior is to use concepts from nonlinear elasticity in combination with experimentally acquired data, as shown in these two papers. An alternative approach that enjoys widespread use in computer animation is to use strain limiting, which combines a soft elastic material with hard constraints on maximum allowed deformation. The idea of strain limiting goes back to the work of Provost, who experimented with mass spring simulations. He corrected for artifacts from low stiffness simulation by iteratively adjusting vertex positions after every integration step. This idea has been widely successful and was used and extended in numerous works. For example, Bredesen et al. Integrates strain limiting and collision handling as layers in a velocity filtering stack. Tomasevsky et al. Extended the strain limiting to continuum mechanics setting by enforcing bounds on entries of co-rotated Kersey strain tensor. Subsequent work introduced limits on the principal strain to achieve isotropic and anisotropic behaviors, and propose extensions to quadratic strain measures. All the above approaches enforce strain limiting by iterating over individual springs and elements. Its convergence is slow, and there are no formal guarantees on convergence. Another line of work aimed at globally coupled enforcements based on constraint optimization techniques. While this strategy can greatly accelerate convergence, existing methods either solve only a linearized version of the problem or resort to nonlinear programming techniques to deal with potentially non-convex constraints. In either case, there are no formal guarantee on convergence. So in this paper, we propose a new approach to strain limiting based on second-order cone programming, SOCP. Unlike previous mentioned methods, our formulation gives a convex optimization problem and is guaranteed to have a unique solution. Our formulation can treat anisotropic bonds on stretching. This problem can be solved much more efficiently than Gauss-Seidel method and generate nonlinear programs. For time stepping, we further propose a constraint reflection scheme and show that it exhibits superior energy conservation property compared to conventional end-of-step projection methods. So let's start the theory part and describe how we derive the SOCP for strain limiting. In our simulation, we consider discrete elastic surfaces represented by triangle meshes with deformed and undeformed states. Using a finite element discretization over the space, the deformation gradient F gives the map between the undeformed and deformed states. It's evident from this expression that F is a linear function of the deformed positions, which we refer as K inset for our following derivation. With the deformation gradient F, we can quantify the direction deformation for any unit length material direction as the squared length of the transformed vector. Based on the definition of deformation gradient mentioned in the last slide, the F is a linear function of the deformed positions. So this deformed vector D is also a linear function of X. So we can write it as A times X. Therefore, we can rewrite the above equation as the following form. Based on the definition of the directional deformation, we can now write the deformation limits as quadratic constraints, where Bi is specified deformation limits in the corresponding direction as shown in the bottom figure. Therefore, we can do the strain limiting by projecting candidate positions onto the constraint manifold by computing the closest configuration that satisfies all constraints. We can see this strain limiting projection is a quadratic constraint quadratic program. For the stretching strain limiting, A transpose A is a symmetric positive semi-definite matrix. So this QCQP is convex, therefore it has a unique global optimum. Geometrically, we have this convex set as shown in the bottom. Well, for compression strain limiting, imposing low bounds on deformation corresponds to multiplying the quadratic constraints by -1. Therefore, negative A transpose A is a negative semi-definite matrix, and the constraint is no longer convex. Geometrically, this bilateral version of this constraint is non-convex, since the line connecting the 2 points does not belong to the feasible set, as indicated in the red line. So we do not consider the compression strain limiting here. These observations that are valuable as they assert that our projection problem, which enforces bounds on stretching but not compression, has a unique solution. This is a crucial property that previous formulation did not possess or expose. However, in order to leverage full computational advantages that this setting offers, we must transform this QCQP into a conic formulation. Before we convert the QCQP into equivalent SOCP, we first introduce several definitions in conic programs. Conic programs are optimization problems in which inequality constraints are expressed as set inclusion condition on convex cones. We mainly focus on quadratic cones. Here we have L2 norm smaller than a variable t. Geometrically, it shows like a cone in the right side. While quadratic cones directly allow for Euclidean norm constraints, it's often more convenient to impose constraints on squared norms. To this end, we use the so-called rotated second-order cones, and it looks like this one. With the definition in the last slide, let's start reformulating the quadratic objective function. We first write out this as this form, which we basically expand the squared term, omitting the last constant term and introducing an additional auxiliary variable t0. This quadratic objective is equivalent to the following form, and then we can easily formulate it as the corresponding conic form. Similarly, by introducing 2 additional variables ti and yi, the quadratic constraint is equivalent to the following form. Therefore, we have combined conic form of objective and the constraints as following. With the above formulation, we have converted our constraint projection problem into SOCP form. It is therefore guaranteed to have a unique solution, and that solution can be computed with any SOCP solver. When implemented as a post-step velocity filter, our SOCP formulation integrates seamlessly with standard timing stepping schemes and collision response method as shown on the right side. The step and projection approach first take an implicit order step to X hat, and then project to the constraint manifold, as shown in the bottom. It's generally lead to stable and visually pleasing motion. We notice, however, it's largely inherent numerical dissipation of low-order implicit integration schemes, which manifests as a loss of kinetic energy and dynamic detail over time. So to improve the time integration scheme, following the idea by Zenter et al., we experiment with a quasi-symmetric constraint reflection scheme that we referred as step and reflection, SAR. So to this end, we first integrate to the middle of the time interval, where we enforce constraints by solving SOCP. We then apply twice the correction required to satisfy all constraints, which visually reflects the current configuration to the other side of the constraint manifold. We step from this reflected configuration to the end of the interval, where we apply a standard constraint projection at the end. The rationale of this step and reflection scheme is that in analogy to symmetric integration schemes, the quasi-symmetric arrangements of constraint correction and integration steps should lead to better energy conservation. So as can be seen in the figure, we indeed observe that the reflection scheme SCA in green lead to better energy conservation. Unlike implicit solar and step and projection approach, the plot also shows that the energy evolution for the step and reflection scheme shows slightly oscillation around the Earth's mostly evolving curve. We conjecture that this behavior might be akin to the fluctuation observed in symplectic integration schemes, which, although non-monotonic, exhibit excellent long-term energy conservation. We additionally experimented with BDF2 variants of our end-of-step projection and reflection schemes for comparison. The energy curves of BDF2 methods exhibit larger fluctuations, but show overall better energy conservation as expected. Finally, we also investigate the impact of step size on our SAR method. As can be seen in this figure, SAR is robust even for large step sizes, even though energy conservation deteriorates. Here is the simulation results for implicit solar without strain limiting, our step and projection, and our step and reflection. We can see the simulation by step and reflection is stable and show better energy conservation. Our method allows to freely impose arbitrary bounds on stretching in any material direction. Here we show the simulation results and different isotropic strain limiting. Here we show the simulation results of orthotropic fabrics with tight and loose bonds in different directions, as well as fully anisotropic waves. In all these experiments, we observed that our SOCP-based method is very robust, yielding stable results for these dynamic examples that precisely satisfies work constraints, regardless of deformation limits. Finally, we analyzed the performance of our method by measuring the average time of our SOCP solver using different mesh resolutions. We use Newton solver for implicit solar as a reference, as can be seen from the table. The timing for our method and implicit solar are comparable for small and moderate problem sizes. For larger problems, however, computation times increases much more rapidly for SOCP, taking roughly 4 seconds for about 10,000 degrees of freedom and approximately 30,000 inequality constraints. To further analyze the performance of our method, we compare to two common strain limiting methods. The first one is solving a general nonlinear programming problem, and the second one is using Gauss's saddle to iteratively enforce constraints per element. As can be seen in the table, our methods stand out over these two alternatives, especially for high-resolution meshes and tight deformation bounds. In addition, we can see that both NLP and JS may not converge or even fail to handle the problem for high-resolution meshes. In contrast, our SOCP solver handles all these cases robustly. Conclusion, we present a new formulation for strain limiting based on second-order cone programming. Our formulation is convex, so it's guaranteed to have a single optimum. With arbitrary anisotropic stretching strain limiting, we can model a large range of intrinsic material behaviors. With the conic form, we can leverage powerful conic programming solvers to efficiently solve our problem. Our experiments indicate that our SOCP-based approach is robust, yielding stable and temporarily smooth animation, even for tight deformation bound. Limitation and future work. Our SOCP cannot handle bounds on compression since corresponding constraints are not convex, as mentioned before. We argue that for thin sheet materials such as textiles, it is worthwhile compromise as compression generally lead to immediate out-of-plane buckling. Computation times go rather rapidly with respect to mesh resolution. However, our method still outperforms conventional approaches by large margins, especially for high-resolution meshes and tight deformation bounds. So multi-resolution approach that enforces constraints on coarser levels than the simulation mesh might be a worthwhile direction for future work. We have demonstrated that our method can be combined with simple collision response approach. However, future work should investigate ways of integrating our method with advanced collision handling frameworks. Here we focus on in-plane behavior. It would be also interesting to develop quadratic formulations for bending deformation limits. Okay, thank you. Thank you for your attention.
Questions? It's getting late in the afternoon. Cool. Going once, going twice. All right, cool. That's fine. Thanks for the great talk. We'll go ahead and move on to our next speaker, I think. Thanks again.
Okay, thank you. Okay.